Okay, we're going to consider another problem, and this one will be a car going around a curve. So here we have a car that's on a straight section of road. Then the road curves, and we'll assume the road is circular right here, the radius r, and then it reaches a straight section again. And our problem will be, we want the car to be able to round this curve without skidding. And we will be given that the radius is r, and here we'll give it a specific value. We'll know the coefficients of both static and kinetic friction. We will assume the road is perfectly level, and what we want to find out is how fast can this car be going as it makes the curve, and we'll assume that the speed will be constant as it goes around the road. And our problem is we want the car to make that turn without skidding. We're going to solve this problem the exact same way using the exact same procedure. So the first thing we're going to do is identify the free body diagram. So what I want you to do is sketch a free body diagram of this car because it goes around the curve. And what I've shown right here is actually looking at the car from the rear but level with the road. Okay, forces that will be acting. Well, first we're going to ignore air resistance. Cars can move fast enough that we may need to worry about air resistance. We're going to ignore it for simplicity's sake. Then we'd have to worry about the cross-sectional area of the car and its drag coefficient and whatnot. So we're going to ignore air resistance for the time being. Also here, we don't have to worry about tension because there are no ropes or cords attached to the car. So all we have to worry about is weight, normal, and friction. Now, notice centripetal force is not listed here. Centripetal force is not a type of interaction between physical objects, and those are the kinds of forces that belong in a free body diagram. A centripetal force is just another name for the net force that causes an object to turn. We don't give a name for a type of force, a propulsive force that makes something speed up or slow down. But we do give a name for forces that make something turn because prior to Isaac Newton, people didn't realize that a force was required to make something turn. So therefore, to emphasize that that is in fact require a force, we give it a name. But it is not a type of interaction between physical objects. It does not belong in a free body diagram. Another important point is to note that we do not have an inward centripetal force counterbalanced by an outward centrifugal force, which might be called mv squared over r, and those two forces counteract each other to keep the car going at a constant speed, because there is a non-zero net force acting on the car as it turns. There has to be. Otherwise, it wouldn't be accelerating. If there were an inward and an outward force that counterbalanced each other, the car would in fact be going in a straight line and would not turn. So we do not have both an inward and an outward force acting on the car. Instead, what we have is just gravity pulling straight down, the normal force pushing straight back up from the road. Because the road is level, these two will be equal and opposite. And then we have the centripetal force caused by friction, which will be pointing inward towards the center of the circle. So those are the only three forces that we have. There is no outward centrifugal force, and there is no separate inward centripetal force. Now we need to pick our frame of reference. Here, because we have a curve, what we're going to do is basically take y-axis and make that vertical, and the x-axis is really just going to point towards the center of the circle. Or in effect, we're closer to using polar coordinates rather than Cartesian coordinates, so that the frictional force will always point towards the center of the circle, not in a fixed direction. So we're going to be considering x-axis will really be pointed radially inward towards the center of the circle, and the y-axis will be vertically upward. So there is our frame of reference, and of course it'll be attached to the ground to be an inertial one. Now what we need to do is apply F equals ma to the car. X points radially inward, so the only force pointing radially inward will be friction. That equals mass times acceleration. And here the acceleration will be a centripetal acceleration because we're going around a circle at a constant speed. So A will equal v squared over r. In addition, in the y direction, the net force must be 0, and that's just the normal force minus the weight. Note, technically the mass of the car was not given. We don't know what it is. As a result, when we do the math and actually calculate what the speed is, we're going to have to hope that the mass ends up canceling out somewhere along the line. So that's just something we need to look for. We'll leave mass in here for the time being, noting that mass is not known. Now, the next thing we need to do is apply constraints in our force laws. Well, the force law we need to worry about, of course, is friction. And the problem we're going to have to figure out is, should friction be static or should it be kinetic? So a question will appear, and I want you to take a guess. Are we dealing with static or kinetic? Well, you might guess it's kinetic because the car is moving, and moving, generally speaking, means kinetic friction. However, while it is moving, I don't want the tires to be sliding relative to the road, and I want them to stay in place via static friction. As the car moves forward along the direction the tires are aimed, I don't want them sliding, if you will, either in or out towards the center of the circle. I don't want them sliding horizontally this way. And the reason they won't is if static friction is strong enough to make the car turn without making the tires skid. So therefore, what I really want is static friction. I don't want kinetic friction. In addition, what I really want is I want the tires, if you will, to grip the road. That's generally speaking called traction. And traction is just friction that's, if you will, good. It makes your car accelerate. And here I do want the car to accelerate, but accelerate not in the terms of speeding up, but accelerating in the terms of turning or changing direction. And that traction will be the static friction. And static friction follows this relationship, namely the value for static friction must be less than a maximum value. The maximum value is given by the coefficient of static friction times the normal force. We now have all of our equations, so we'll gather them together. F equals mv squared over r comes from Newton's second law. N minus mg equals 0 also comes from Newton's second law. Then we have our equation for static friction. And to remind you, these are the values that we started out with. So what I want you to do is calculate a value for the maximum speed that the car can have while going around the curve. One way to solve these problems is to take this one right here and solve for the normal force. So notice in this case, the normal force is just equal to the weight. So we can plug that in right here. The normal force right here is simply equal to weight. In addition, we know what the frictional force is. It must be mv squared over r. So we plug this in right here, this expression for F, and this expression we plug in for N. That gives us this, namely mv squared over r must be less than mu sub s times mg. And note, in fact, we have m on either side of the equation. The m's will cancel out, so we don't need to worry about the mass of the car, which is what we were hoping for. We can then solve this inequality for the velocity, and the velocity must be less than the square root of mu sub s times rg. And then we can plug our numbers in and find out that the velocity must be less than 44.7 meters per second. And that is our answer. So that's as fast as the car can go. So long as the car is moving less than that, it will make the curve without skidding. And this is actually a fairly high velocity, so this is a curve the car can easily make. Finally, we need to consider, does our answer make sense? Note that the velocity should have the units of meters per second, and our expression was the square root of the coefficient of friction, which is dimensionless, times a radius times g. And that expression does indeed give us meters per second. So our velocity does in fact have the correct units. Dependencies. Well, notice as friction increases, as mu increases, the car in fact can round the curve faster, which should make sense. As the radius increases, now that means the circle will be larger, or the turn will be more gradual. It will be a slower change in direction. That should be easier to do. And the car, in fact, can then round the curve while going faster. It's easier to round a gentle curve than a sharp curve without skidding. Now, the mass turns out to be irrelevant because the net force, which is friction, depends on the car's weight via the normal force. In addition, the acceleration also depends on the ratio of the net force to the inertia. Well, the net force depends on the mass. The inertia is the mass, so we've got mass divided by mass, and mass will cancel out. The mass of the car does turn out to be irrelevant. So our answer should make sense. We're done.